So the purpose of this video is to choose the best airfoil for the low Reynolds number. And we know that there is plenty of different airfoils, like those for instance, and the goal is to choose the one which is best fitted for the low Reynolds number. First, we have to decide actually what is the real number is. I have this beautiful graph I have borrowed from someone. I have to make a remark that I have background in aerospace engineering only a few weeks, so I heavily borrowed material from other people. So this graph is from some book, I guess, and from here we can see that different flying objects have different numbers. For instance, insects have a lower Reynolds number, approximately 100, and the Mach number is even less than that. And my goal is to basically build a plane which is size of the bird, so the number is approximately 10 to the power 4, 10 to the power 5, and the Mach number is 0.02. So those number. Or we can do it in a more complex way. We can use this equation and compute the number from the first principle. So we have the parameter for the atmosphere, so we can plug those number in and get the result. But the key thing is that the Reynolds number is proportional to the speed of the air and the characteristic length of the object. Like in our case for the wing, we have the length is actually the chord length of the wing. Okay, so once we know the numbers, we can move to the simulation. And I haven't written my software yet, so I have to use somebody else's software. So I take a look at different software which is available on the market, and I chose the XFOIL. That's a free software written by those marvelous people, and you actually take a look at the academia. They have publications there, so we can take a look. So it's pretty good. So for instance, this publication of one of the creators of this software, it's very good written and lots of information which can be used for the study. So so the goal was to choose the software, and the main idea was to choose the software which is a command line, so I can use basically batch programming, and I can create automatic scripts to simulate many different airfoils at once, so I don't have to enter each airfoil separately. And the second requirement was of course the Viscous solution. So basically a solution for the wet water. So the simplest case, if for the high Reynolds number we can ignore the Viscous solution. And for instance, we can do it very simple, just basically solving Laplace equation and then mapping it to the particular airfoil shape and eventually find the performance. But for the low Reynolds number, you have to find the Viscous solution, Viscous law, and this is not a trivial task. So lots of effort have to be put to write the software, and the best solution is to use the software which have been written already. So this software is 30 years old and probably is the best available at this moment for this application. Okay, so the boundary layer. So Viscous solution meaning that you have to study the behavior at the boundary layer. So wet water or the wet air means that the molecules of the air are actually sticking to the surface of the airfoil, and the speed drops to 0 at the surface. So if we initially have the airflow with same equivalence speed, then when it's start to face in the airfoil, the speed at the bottom start to decrease and drops to 0. So we have 0 speed at the tip, at the surface of the airfoil, and then it increases a bit when we move up. And then we also have the formation of very interesting objects, so the vortices. So speed basically drops to 0, and then eventually start to go to the opposite direction. So meaning that the air starts to circulate and moving in opposite direction. So this has to be included in simulation as well. So the XFOIL software does this beautiful job for us, and we have the solution. And we also can write a script to simulate plenty of different airfoils at once without necessity to enter it manually. And we will see it in a moment. So the XFOIL software is open, and it consists of 2 windows. So the first window is the DOS prompt. It's a command line software, so we just type the commands here, and then the results are shown in separate window. So we have 2 windows, and we can start using this software. To see what commands we have, just type question mark and enter, so we can see different options available for us. For instance, we can load, save, load airfoil, save airfoils, and so on. So the commands are self-explanatory, just read the description or read the manual. But the first step is to load the airfoil. And the easiest way to do it is just to load the built-in airfoil. In XFOIL they have several, not several, but they have NACA airfoils profile built in. So the NACA profiles are constructed by the parameters. So if we type, say, NACA 0012, we have the airfoil constructed, and we have the parameters of this airfoil once loaded. So at this moment we see that the number of panel nodes and the ratio between the trailing edge and leading edge panels. So to see actually what we have loaded, we just type ppr, and we see the profile, and those points actually show the discretization between the nodes, and the more points we have, the more refined solution we can find, more precise solution. But let's change, let's say distance between those nodes. If I type n, it's number of panels, and let's say use 100. And I also can use a different ratio between trailing edge and leading edge. So if we type t 0.1, just to see the difference. Okay, and now we know that we have the different number of those panels. It's only 100, and we have the different ratio between the trailing edge distribution of panels and the leading edge. So this leading edge more panels on the leading edge and less on the trailing edge. But actually the interesting stuff happens on the tip of the profile and on the tail. So the good idea is to use the same ratio. So we go back, type t equal to 1, meaning the same ratio between trailing edge and leading edge, and we also increase the number of points, say 200. Okay, so we have more points and we have the same ratio between the edges. And now what we do, we can go to the simulation. So use command oper. So direct operation points. So let's type oper. Okay, and now the simulation is going to be run in Viscous mode. So the trivial solution is going to be found. So if you type command cp, we have the simulation of the density distribution on the airfoil. So we have the one graph for the top and the one from the bottom. And we have alpha 5 degrees. I typed this before, so it's we can change the angle of attack by typing, let's say, alpha 1 degree. So now we have the different profiles for the distribution of pressure on the top surface and the bottom surface of the airfoil. Okay, but as I said previously, the Viscous solution is not what we need for the law of Reynolds number. So we have to go back and use Viscous mode. So we type Visc, and now the Viscous solution is running on those numbers. So let us change the Reynolds number. So 100,000 is the Reynolds number, and now we can run the viscous solution. Yes, and one more note that once we are in the viscous mode, we have the V index appearing after the oper command, and previously we have the I. So the I meaning that in viscous mode, and V meaning that viscous mode. So let's type the CP, and here is the solution. So it doesn't converge for whatever reason. So we increase the number of steps. Let's say 1000. Change alpha. 5. Okay. So what we have now, we have the yellow line at the top. And here's the graph corresponding to the top of the foil, the pressure at the top of the foil, and we have the blue at the bottom, the pressure distribution at the bottom, and we see the blue line, the blue graph on the same graph. We also have the dashed line, which stands for the inviscous solution. So we have the inviscous solution and we have the viscous solution. You see the difference happening somewhere there. So let's maybe change alpha a bit. How about 10 degrees? Okay, so now it's more definite. So at this moment, angle of attack is 10 degrees, and we see the difference between the inviscous mode, the dashed line, and the viscous solution. Blue line here, and the same is there. So the yellow line at the top of the airfoil, and the dashed line is actually the viscous mode. Okay, so this is simple, and now we can do more. In viscous mode we have more plotting options. So we can type command BL for the boundary layer, and at this moment we know that we have these beautiful green lines appearing on the surface. So what this means? This is actual distribution of the speed of the molecules as a function of height from the surface of the airfoil. So we can zoom in particular airfoils at particular distributions by typing Z command. And now you have to choose where you what you would like to increase. So now we can see the distribution of speed. So the vertical line is actually the height, and the green light is the speed. So at this moment at this height we have the speed which is actually approaching the speed of the free stream, and at this point it drops to zero close to the surface of airfoils. The same is here. Okay. Okay, but I would like to see the vortices formation. So to do this, I'm going to change the Reynolds number. So first let's unzoom it back, and let's change the Reynolds number. So 10,000. 10,000 is quite a low number for our purposes. And now let's change alpha. So 5 degrees back to 5 degrees. Okay, so we have the graphs, and let's do the boundary layer plot. Okay, yes, I think I have it. So at this moment we note that we have the separation of areas previously. So basically what we have those graphs shown is actually the profile, the effective profile of the airfoil. So this is the effective thickness of the airfoil. So meaning that at this moment the air starts to separate from the airfoil, and separation continues, and then we have the trailing edge small vortices formation. So let's zoom in and see actually what those graphs are showing us. So let's look at this region, and now we have it. So we have the height graph, and we have speed distribution, and we know that in this moment speed going to the negative value. So we have the speed is 0 at the surface, but then speed gets a negative number, meaning that it moves in opposite direction. So we have negative, then it's come back to the normal speed and continues as usual. So what happens here, you have the vortex formation like this and like that. And if you look at the textbook graphs, we know that actually that what is expected in real life to have this kind of behavior. So the formation of vortices and the circulation of air happens on the surface of the airfoil. XFOIL is fun to play with those boundary layers and to see actually what happens on the surface. And we can also see different graphs. So at this moment, if you go to the operation menu and type VPLO, and we look at the comments which are available in this menu, you know that it's a very useful comment to plot the dissipation coefficient. So to look at the drag which is happening due to the viscous flow, you can type the CD command in the VPLO menu, and now you have it. So what this coefficient shows, it's actually proportion to the local energy dissipation rate due to the viscous shear and the turbulence mixing. So it's a very effective way to actually look at the physics of the process. So the drag happens due to the dissipation of energy, basically. And this graph is useful, and we know that, for instance, at the very tip of the airfoil, approximately 0.1, even less, we have a strong increase in the dissipation of energy. The same happens on the trailing edge. And as previously, yellow one is on the top surface and the blue line is on the bottom surface. Okay? So if you type once again and go back to our plot initial, so the dissipation of energy happens here on the tip of the airfoil and on the tail. So what else we can do? The second comment, which is very nice to see, because at this moment we see the density distribution on the air surface, meaning that we have the pressure normal to the surface of the airfoil, and this normal pressure is plotted at the graph, yellow or blue one. So, but how does it actually look like? We can do it by typing this command CPV, and tada, we have the arrows pointing to the normal to the surface and pointing to some direction, to the direction of the surface, and the length of those vectors is actually the value that we have seen on the graph before. So this is the value of the CP, the pressure, and here is the actual result. CPV. Okay. So this is the main not feature, but the key element of this software. Yes, I have plotted a few graphs previously, so I can show interesting features with those graphs. So this is the airfoil, and then we have the upper pressure distribution, the yellow line, and we can know that we have some steps on this graph. And it's kind of not clear what's happening here, because we have the sharp step down. And if you look at the green lines, the speed distribution, you also don't see the difference. Not sure what's going to happen in here. But if you plot the CP, dissipation coefficient, then you will see that there is a huge increase in energy dissipation at this point. So we have this step here, and then we have the dissipation point. So the energy dissipates at this moment. So I assume that some kind of vortex is formed or whatever. The same is peak here. So it's nice to see actually what's happening at the same time. When you look at the CD graph, the dissipation coefficient and the pressure distribution coefficient. So it kind of give you insight into the physics of the process that is happening now. So the dissipation of energy happens on two major points on the upper surface. So here and there. And we also can look at the visual pressure distribution. So we have the vectors here. So we have the pressure happening here, and then after this dip, the pressure drops. That's useful. And here is the graph I have plotted for the difference between viscous and viscous mode. So when you see it for the same picture, the same graph, two solutions, you can see the difference. And why you should use XFOIL, not some other software, without the option to find solution for the viscous mode. So for this case, I have the airfoil in the shape of a plate, and this is the solution in viscous solution. So we know that actually the pressure blows up at the tip of this plate, and also blows up at the end. And then we have the viscous solution. And the viscous solution is far way more, I would say, physical. You don't have like strong jumps at the tip and the end as well. It's more or less steady, and we also have the separation of the flow. And to see the pressure distribution as a vector graph, we have those two nice images. So again, the arrows are basically blowing up. The scale of this figure is different because we have a small size of this plate. And this graph, if you put it there, it's going to be like this. So it's definitely different. And the solution is very different as well. And the number for the lift coefficient is different, and so on. So the viscous mode is the way to go. And there is one more thing, is the n-critical number. So this number defines when the transition happens from the laminar to the turbulent flow. And this number is used in the method called e to the power of n method. Basically, this number shows, this number is the log of the amplification factor of the most amplified frequency which triggers transition. So it's the part of the method that have been used for the simulation of the viscous flow, and we can look at the application. Of this number. So the number might be different. Let's say for the sail plane, it might differ from 12 to 14. For the motor glider, from 11 to 13. For the clean wind tunnel, from 10 to 12. And the default value is 9. And for the dirty wind tunnel is from 4 to 8. Okay, so how to change this number? So we go to the upper menu and then go to the VPAR and change this number. Let's do it. So we go to the VPAR menu, and now we look at the default value. So the default value is 5 at this moment. I have changed it previously. So let's put it back to the default value, which is 10. And the command for this, if you don't know, you just press question mark and enter. So the command for this number to change is n, change the critical artificial. So let's type n and let's type 9. Okay, so it's changed. To make sure that we have it different at this moment, we type p.1 once again, and then you see that the critical number is 9. Okay? Now we're ready to run the simulation. Is this different number? So we can call it CP. We call it go back. Press enter to go back. So we are back to the upper menu, and now we can type CP. What I have to unzoom it, and the solution does not converge because we have changed the critical parameter, and the way the XFOIL works, it uses the previous solution to get the new solution. So it uses previous solution as initial guess for the simulation. So to go back to the default value, we type init. It's a very important comment we have to keep in mind, and always type this comment whenever you change the alpha. Okay, so now we can run the simulation. So it says that BL will be initialized on the next point. Type CP once again. Let's change alpha. I think it doesn't recognize. Okay, so now it converges. So we have the solution ready, and we can look at the boundary layer, look at the separation, where it happens. Let's zoom it in. Well, I increase the critical number, and I see that the vortices start to form a bit closer to the tip of the wing. So meaning that the turbulence happens a bit more. The turbulence is kind of likes to happen as soon as it can. Okay, so we have the turbulent flow at the very tip to the wing, and then we can conclude that this number is actually defines the formation of the turbulence flow. Okay, so I have plotted a few graphs previously, and those are the graphs for different critical number. So this is for number 9, default value. So we have the step here, and we have the jump in the pressure, so meaning that here is the vortex is formed, and the pressure is a bit smaller. And we also note that this step corresponds to the step here, and this step corresponds to the, as we have seen previously, to the dissipation of energy which happens. So this is point for dissipation of energy to happen, the point for formation of vortex, and the point for the jump in the pressure. Well, basically, this graph and this graph are kind of the same, because this is the pressure graph, here is the pressure as well. Okay, so we go back, we go from 9 to 14. At this point, the critical is equivalent to 14, and at that moment we have a huge step, bigger than we had in the previous case. And this huge step means that we have turbulent flow happening more rapidly or at more early stage. So we have, if you look at the green lines, it's kind of small, and now we have big distribution happening there. And probably the more energy dissipation is also happening at this point. And now we go back to we move to the critical equivalent to 5, a very small number. And now we see that it's a very small step and very small drop in the pressure. Okay, so this is useful parameter, and we have to keep it in mind for the simulation. Depends on the condition where we simulate. So if air is clean and steady, maybe we can go with the higher critical number. I mean, with the low critical number if it's a big plane or maybe the sail, then we have to increase the critical number. Okay, the great work was done, and now we are ready to save the data for the further analysis. So staying in the upper menu, we can save the pressure distribution data, and we can do it with the command cpwr, and the file name is, I will open the file browser. So the file name is cp. Boom, you see it appeared here, so it appears in the root directory of the software. So next we can dump many other information, other data. So if you look at the graph, you know that we have many parameters, let's say lift coefficient, drag coefficient, lift drag coefficient, so we can save those parameters as well. And to do that, what we can do, we can type command dump and the file name. I'll call the file dump. And look here, it's going to appear in a moment. Boom, dump file. Now we can go to the top menu by pressing enter. So we back to XFOIL data, and we can save the airfoil. So the airfoil we have been simulating this work. To do this, what we type is save and file name. So save, and we had NACA, I think, to make sure, NACA 0012. So we type NACA, the file name is 12, and boom, it's saved. And here is the NACA profile. We can look inside those files. So let's look at the CP. So we have the X, Y, and CP, meaning that we have points on the X and Y axis, and then we have the value of pressure. Dump file contains information, different parameters, X, Y, and different things that might be useful for the analysis of the airfoil. We also have the airfoil itself. So basically X and Y coordinates for the airfoil. Okay, we have the data, and the next step is to use maybe Python to plot the data and see actually what this data actually is. So let's go to the Python, and here is my Python code. So what I do here, I read the file that we have saved, and then I use this command from the NumPy script. Load this data, and I just can skip few rows just to get the raw data. So once this is done, I put the data into the vectors X, Y, and CP vectors, and I can plot the figure. So what we do, we plot the X, Y, and we receive our beautiful airfoil. Or we can also plot the pressure distribution along the X axis. So I have the X axis, and I have the CP on the Y axis. So X and Y give us the airfoil, and the CP gives us this plot that we have seen in our graphs previously. So this graph is the same. Yeah, and we can also split the bottom and the upper surface of the airfoil. So I'm splitting this data, and then I can plot it in different colors, red and blue. So this is the CP data, and this is, and now it's the dump file. Let's put the dump file. So we load it again in the database, and then we take the vectors that we have as X, Y, UV, lots of data, separated into two subvectors by using this condition. So if Y is greater than 1, then we have it's red, or if it's less than 0, then we have it blue. If Y is greater than 0, it's red, and lower than 0 is blue. So this is the function I have been using for the simulation, for the plotting the data, and in this function I can submit the vectors that I have. So if we submit y-axis, I'm going to have this graph. So we know that it's not just simply airfoil, but also the region behind the airfoil, which is plotted. Because simulation is not ends up on the edge of the airfoil, but continues back. And lots of interesting things are happening behind the airfoil. So this is profile. Then we plot UV data, upload the as parameter. Actually, I forgot what those parameters stand for. Like I have done it some time before, maybe 1 week before. So I have to take a look. This is friction coefficient, so the upper surface. The friction actually happens not at the very tip, yes, but then it happens when we have seen this jump in the pressure. So the vortex is forming, and we have the drag happening there. And at the bottom it happens just at the tip of the wing, at the nose. Okay, so drag coefficient, again drag coefficient behaves in interesting way. Then we have the theta, that's one of the parameters for useful simulation. H parameter, I think it's the separation of the flow, probably. Where the flow separates. Not sure, I have to check it. So anyways, but this is the way to pull the information from those files and to have the data, and then you can play with this data. And definitely you can see more than you have seen in the default software, graph. So we have profile, we have information behind this profile, we have lots of parameters that we can study. So how many parameters do I have? Actually, I have 1, 2, 3, 4, 5, 6, 7 parameters. Okay, and I think that this is a good moment to stop the discussion for now. Maybe I will continue in the next video.